going to overlap. So if you have something that is badly distorting the fields,
Yes.
then 5 points was not enough. You take a lot more points than that, and you'd start to see, I guess like you see weather maps when they show the pressure bars, and you sometimes get those little vortices somewhere in the middle. I think they're called hurricanes. So you have your equipotential lines, and actually let's drop it back one step further. You have your equipotential lines. We'll just simplify it to 3. And now I have to draw my electric field lines going from here to here. Now this, in a different color. That one's relatively easy, but it gets a little bit tougher the more you got the warps in it. So I'm going off in this direction right here, and I know it's got to cross there. Sort of, I know the general shape of it. You know, something like that. But I've asked you specifically to do the one that goes through your point M, whatever your point M happens to be. So let's say that your point M is there. So I'm drawing a line here. I know it has to cross perpendicular at that point. And you've got something like that. So when I darken it in, I probably do it by pencil at first, but then when I darken it in, so that's your point M. When you draw the tangent line, hopefully you've got some sort of curve there. And so the electric field's going that way. So my electric field would be going, and I'm just drawing a line that just barely skirts the curve. And so experimentally, what's that angle? So if you're on this side, it'll be a second quadrant angle. If you're on that side, it'll be a third quadrant angle. Does that answer your question?
Yep.
Okay. And I have seen some equipotential lines that really make the electric field look really bizarre, which makes the tangent line that much more difficult. Do the best you can.
So is the lab and the master set for chapter 24 due the same day?
Yes.
Okay.
Which reminds me, master set 23.
They've already been read.
Okay. 4 on paper, 2 that have been emailed to me, and some that are missing.
Did you get mine?
Yes, yours was one of the emailed ones.
Was it dark enough?
I didn't get that far. I graded the ones that were on paper. I found this idea of should everything be submitted online or in paper. I find that grading online is much easier at home, but grading on paper is much easier here. So having some one way and some the other way, I think is going to be the most efficient for me. However, I don't think some of you have handed in master set 23. So it's possible it's been misplaced. But if you have not handed it in, please let me know. If you do not let me know, then I will go searching to see if I put it in the wrong spot.
I emailed mine to you.
Okay.
I also.
Then I think yours I haven't, I need to double check that. All right, so anyway.
I did have a question about the stuff we just went over again. So the 100 right there, was that just plugging it into that one bottom equation?
Yeah, that was just straight plug and jump to the bottom equation. Was that it?
Yeah.
Oh, okay.
I was just making sure.
Other questions about the lab? Other questions about the stuff that we just did? Other questions about presumably something physics related?
Estimated due date for the exam.
I think it said the 15th, but I think the 15th is really more.
doing the test one of those 2 days. Test 1A.
What chapter does the book go to? Cause I bought it recently, but I wanna make sure I got the right book.
Oh, what chapter is it? There is a version which has the whole thing on it through
Like 30.
chapter 39. So there's a version that has chapters 1 through 39, and I think, yeah, Mario has that. You can also buy it in halves.
I shared, the PDF document online, if you.
I just found a cheap version. I think it's that one, cause it's big. Cause I rented the small one.
Okay.
But then I found the big one.
Yeah, they should be the same. There was somebody, I'm using the 2016 edition, somebody has the 2017 edition, so it's sold in the bookstore. Somebody scanned some pages and I just matched them up, and everything I saw, they were identical. I'm not sure why there's a 2017 edition and 2016 edition. There might be some typos that got corrected. Any mistakes I made are based upon the fact that I was using an earlier edition. Yeah, let's go with that.
Are you still a fan of Giancarlo or,
What's that again?
are you still a fan of Giancarlo or no?
Assassin was the more of the fan of Giancarlo. I actually preferred Cats. I suspect when they no longer support this one, we'll go to OpenStax is my guess, but I don't know. OpenStax now has a calculus-based version.
Cool.
Won't help you at all, but someone else won't be paying any money for the book.
Who knows?
Unless, of course, you decide to take the course again.
I'm sure it'll be helpful when later on. Thermodynamics is.
All right. Let's do some math problems. Sorry, physics problems. I mean, for the most part, math is just the language that physicists use, but it does actually get to a point when we get to chapter, I think it's 38, where the math actually drives the physics. There's things that pop up in the math that make you go, wait a second, if this equation is true, then this other thing can't be true. And so then they said, well, let's assume that the math is correct. And then that actually drives some physics that has now been supported. And there's also this idea of the electric field. When they first come up with the electric field, they have no idea if it's true or not. It's just a math shortcut. And it's probably another 50 years after they start talking about the electric field before they finally realize, oh, there is something physical that is the electric field. It's more than just something we made up. 4 nanocoulomb charge here, 3 nanocoulomb charge here. Let's put them 5 meters apart. What is the potential in the middle? What is the potential energy of the 2-charge system? Let's go ahead and establish so that if I just left it like this, you could make a legitimate argument, well, the answer is 0 for both, because that's how you define it. However, to avoid that, let's throw in when R is infinity, V equals 0 volts, and U equals 0 joules. All right, Lawson?
Why do you write equations using nanocoulombs and other forms instead of just coulombs when that's what other equations are?
Nanocoulombs is more realistic of what you're going to find. I mean, you probably could get a 3 coulomb charge, but if there were 3 coulomb charge in this room, we probably would all die. So on a more realistic basis, the Van de Graaff generator is microcoulombs. That tends to be why I do it. And also, for finding the potential, just so that our final answer ends up being, what I'm going to call a reasonable number. The fact that I'm not dealing with a whole bunch of zeros one side or the other.
But when we just have to, oh, okay, I get it.
Just like over here, when I did nanocoulombs, we had 108 volts, not 108 million volts or anything like that.
Okay.
Although our potential energy will end up being small. All right, so, let's do potential energy first, even though I asked it second, because that's just straight up plug and chug. I got two charges. Formula K, Q1, Q2 over R squared. We're dealing with scalars, don't have to worry about direction at all. 9 times 10 to the 9th.
Isn't it over R?
Yeah, isn't it?
Thank you very much. Is that the first time we've done it, made that mistake this semester?
2.16 times 10 to the 10th.
It won't be the last. Times 4 times 10 to the negative 9th, times 3 times 10 to the negative 9th, divided by
Would that be 2.5?
it would not be 2.5.
2.16 times.
But hold on just a second, one question, answer at a time. What is the denominator?
Is it infinity?
No,
Maybe 0.
no. I hope it's not 0.
No, I'm saying if it were infinity, it would be 0.
Oh, yeah.
Oh, sorry, I thought you meant 0 in the denominator.
Should be 5 meters.
Should be 5 meters, yeah. The potential energy is of the system. That point in the middle is not part of the system, it's just there. You have the two charges. The potential energy is because of those two charges. So it's over 5 meters. Couldn't have made some things that worked out completely well. So I basically have 12 times 9, which is 108, divided by 5. So that is 21.6
Yep.
times 10 to the negative 9th. It's so, oh, I said yeah.
Yeah, that's right. Well, the way that, I mean, it's the same thing as 2.147 times 10 to the negative 8.
Oh, okay. However, that's not the pause here. That's not the dramatic pause for effect. Thank you. Somebody might have said it and I just missed it, because, on me. But, Jules. Or 2.16 times 10 to the negative 8. All right, so now the potential, the electric potential right smack dab in the middle. Our formula for electric potential, KQ over R, plus some constant, but I eliminated the constant by establishing where 0 is. How do I deal? I have two charges here, so what am I doing? Yep. So I've got 9 times 10 to the 9th, times 4 times 10 to the negative 9th. Now, Austin, what's our?
2.5.
Plus 3, that's still 9 times 10 to the 9th, times, I guess we have to do the 3 times 10 to the negative 9th, over 2.5. At 14.4 plus 10.8. Okay. Not complete yet. Finish it off.
Joule per coulomb.
Okay.
Cool.
So for the shortcut, but joules per coulomb is absolutely right as well. change it around just slightly. Oh, questions on this before I change it around slightly? Let's make that negative 3 nanocoulombs. What changes?
Negative voltage.
You said voltage, we're not dealing with voltage.
You have negative potential energy.
All right. The negative goes right here, which makes that negative and negative.
For electric potential, you would take the difference of 14.4 minus 10.8.
All right, that becomes negative, so that becomes negative. So 3.6 volts. Let's change it around just slightly more. Any questions on this before we change something?
Where's the top of this?
We're getting there. Austin, this one's for you. I put a 6 coulomb charge right there. Then, get that 6 coulomb charge to move over here, and let's make that, where have I not used, let's make that 2 meters from there to there. What is the electric potential at the new spot? Because of these 2 charges here, not the 6 coulomb, but the other 2. Well, all that's changing is the denominator here. So we end up with 36 over 7 plus, oh, let's keep it negative 3. Negative 27 over 2. Someone with a calculator?
Wait, can you explain what you just did? You moved the different charges where?
I have the 6 coulomb charge here, and it moves to this point over here, which is 2 meters away from the negative 3 nanocoulomb charge.
Okay.
That's all I've done. I've introduced a new charge and it just moved it.
Where'd you get the 36 and the 20?
Oh, the 9 times 4, and then the 9 times negative 3.
Okay.
Those aren't changing. What's changing is the denominator.
Negative 117 over 14. Negative 117 over 14.
Good. You said volts? Good. That's not an X, that's a V. All right. So what is the voltage that 6 coulomb charge was sent through? In other words, what's the electric potential difference between these 2 points? Well, the voltage is the final potential minus the initial potential, because that's what change always is. Negative 117/14 minus 3.6. And it's 3.6 instead of 25.2 is because I kept the negative in there.
Negative 11.95.
Did you say 4 or volts?
Volts.
What's the change in potential energy for that 6 coulomb charge? Well, delta U divided by the charge is equal to delta V. And so delta U, just U delta V. So 6 times negative 11.95. Which is negative 71.7. Right. Now Mario asked for some calculus. Let's do some calculus. Questions before I erase? We did something similar with electric field. Now we're going to do is find the electric potential. Again, let V equals 0 volts when R equals an infinite distance away. Make that 5 meters, make that 2 meters. Uniform linear charge density. And a total charge of 4 nanocoulombs. I have some point P right here, and what I want to know is the potential, the electric potential at point P. Well, charge distribution. So we start out just coming up with an infinitesimally small bit of charge. dq. We find the electric potential because of this charge right here, and then we integrate over all of those differentials. I'm going to define x as being the distance from here to here. That is x. Because why not? I'm plugging into basically the point charge formula because I'm creating a point charge here. So my point charge is not q, or little q or big Q, it's dq. Certainly want some ice cream. So it's k dq over r. I don't have to worry about directions, vectors, or anything like that. That's 9 times 10 to the negative 9th. Probably a little bit early for that, sorry. Keep that out. So V would be the integral k dq over r. I have two variables here. I have r and I have q, are both variables. I know q is a variable because, well, it's the differential, it better be a variable. Uniform charge density here, that's equal to q over L, or dq over, I'm dealing with x there, dx. So I make that substitution. So this is lambda dx. And r is the distance from this point to my differential, just 2 plus x. Or for those feeling a little bit saucy, x plus 2. I now have a single variable. I can now do my limits of integration. And what are my limits of integration?
X minus R to X. 0 to 5.
I guess I have it in terms of x here. The smallest value of x to the largest value of x.
Do you remove lambda?
I pull it out front, it's a constant. And the key that I know it's a constant is the keyword there, uniform. So I now have k lambda up front times the integral from 0 to 5 of dx over 2 plus x.
Use substitution.
Yeah, but we're still left with what's du over u, integral of du over u, natural log. So this becomes k lambda, natural log of 2 plus x from 0 to 5. Lambda, well, we have this charge per length, so this becomes k q over big L. Let's go ahead and define big L right there. Times the natural log of 7
9.014.
minus the natural log of 2. So we have 9 times 10 to the negative 9th, times q, which is 4 times 10 to the negative 9th, divided by my length of 5, times the natural log of 3.5.
This is volts.
Say it again?
This is volts or this is energy?
We're finding the electric potential.
Okay. So do we always have to derive it, or should we just jump straight to the limits of integration, like in the end?
If you can skip steps, that's fine. Just please make sure you know what you're doing when you skip the steps. I have seen people in quizzes have memorized the problem so well, they just jump straight to the last formula that they're plugging into. But it means if they remembered something wrong, it's no credit at all. Now, they're skipping everything until the very end. There'd be a deduction if you misremember if you skip smaller steps. Lawson?
Isn't K 9 times 10 to the 9?
It is, thank you. That was an underscore from this.
If anybody else gets 9.01, please tell me.
Yeah.
9.01? Yes.
Where do you get the natural log of 7 minus the natural log of 2?
The integral of 1 over the unknown is natural log.
Mm-hmm.
So the problem was from here to here.
Yeah.
Okay, when I plug 5 in for x, I get 7. When I plug 0 in for x, I get 2. That's where the 7 and 2 come from.
Yeah, I should have seen that and I didn't, so.
Okay.
How do you get natural log of 3.5?
When you're dealing with, it's one of the rules of logarithms, the natural log of x minus the natural log of y equals the natural log of x divided by y.
I didn't know that, okay.
It's how you can do multiplication and division with logarithms.
Yeah.
The essence of the slide rule.
I probably have learned that, I'm sure I've learned that, but I just forgot it, so.
I still get mixed up on which one's the power, which one's the ending result. I'm taking looks.
If you had just done natural log of 7 minus natural log of 2, you'd get to the same place.
That's how I did it.
Yeah. I assume you got to the same place.
Mm-hmm.
I'm right about at least one thing today. All right. Let's see, did that. Ooh. Change this around, I can keep all that stuff the same, I'm gonna move my point P. Two meters this way. So we're now dealing with a two-dimensional problem. But we're not dealing with vectors, so it's not like I need an I component and J component. Unless, of course, the previous problem asked for find the electric field at that point. Which at some point, there are a number of tests where I give the situation and say, find the electric field, find the electric potential. Or one test where I gave 4 scenarios and I said, pick one. Find the electric field and find the electric potential. As before, we find some value of our charge there, dq. R is that distance. I could have left a good bit of what I had up already, but so this is k dq over r. As before, lambda is equal to dq over dl. So dq is lambda d, I guess, x. But what is r? Or how do I want to define x? Where's x equal to 0? Where do you want to make x equal to 0?
Isn't this similar to the infinite plate?
The one we did with the infinite plate required vectors, so sine or cosine. Yeah, it came in the back. So we're not dealing with vectors, so we don't have to break it up into components. That's the big difference. But I mean, the process that we're going through is very similar to the process we've gone through many times.
Could we use Gauss's law at all here?
Gauss's law helps find the electric field. I guess if this line of charge were infinitely long, you could use Gauss's law to find a formula for the electric field, and then from that you could find the formula for electric potential. We haven't gotten that far yet officially in the class, but you could do it that way. But it's a finite size. Using Gauss's law is not going to be the easiest.
What would your shape, what would your surface be, your chosen surface? Is it
Generally, if it's a line of charge, I pick a cylinder from a Gaussian surface.
through the center, or like perpendicular and through the center of the line, or?
No, for the line of charge, I'd pick the,
Okay,
something like that.
okay.
For if the infinite plate, basically
It's
2
good.
cans stuck on a piece of
Right.
paper.
Yeah. I saw that one, I didn't see